So in my last video, I looked at Bernie's claim that if you were trying to build a ladder of people to the moon, you'd eventually reach a point where you'd be building back down to the surface of the moon. And I talked about something called a Lagrange point. And I mentioned that there are a total of 5 of these in the Earth-Moon system. Let's look at these in a bit more detail and see where they come from and why they work. So Lagrange points occur when you have a large object, like the moon, orbiting an even larger object, like the Earth. To make things easier, I'm going to refer to the smaller object here as the moon and the larger object as the Earth. So the Lagrange points are the 5 places in orbit around the Earth where we could have a small object, like a satellite, orbiting the Earth with the same amount of time as the moon. From the moon's point of view, they would stay in the same spot in the sky compared to the Earth. Of these 5 points, only 2 of them are stable equilibrium points. This means that if you were to put a satellite into either of these 2 points, it would be able to stay there relatively easily. If you tried to put a satellite into either of the other 3 points, even a slight nudge would push it out of this position, and it would start orbiting either the Earth or the moon independently. I also talked about how the first Lagrange point wasn't exactly where we would expect it if we were just trying to balance the Earth and the moon's gravity, and I said that this was due to the centrifugal force. I'm sure there are some people out there who are annoyed at this, seeing as the centrifugal force isn't a real force. It's often called a pseudo-force. So that we don't have to worry about dealing with it, we're going to pick a frame of reference where we don't have to worry about the rotation of the moon around the Earth. In order to do this, our best choice is to pick the center of mass of the Earth-Moon system. Because of the way that gravity works, when the Earth pulls on the moon to keep it in orbit, the moon also pulls on the Earth. We see that the Earth moves around the center of mass of the combined system. In this case, it means the Earth appears to wobble slightly, because the center of mass is actually within the Earth. So now that we have our center of mass reference frame, we don't need to worry about the centrifugal forces on an object trying to move within the system. And we can clearly see the way our 5 Lagrange points are also in orbit around the center of mass of the Earth-Moon system. The other things we need to remember are the way that forces affect the circular motion of an object in orbit, and the way that gravity behaves as distance changes. Greater force means that an object needs a faster speed in order to stay in orbit. We also see that as you get further away from an object, the gravity force decreases. This means that orbits further away have to get slower as the force of gravity drops down. This means that under normal circumstances, an object orbiting closer to the Earth, like at our first Lagrange point, would have to move faster than the moon, and would overtake it over and over again as it completes its orbits faster. So how then can our first Lagrange point actually exist? Well, it has to do with the fact that the moon's gravity is pulling against the Earth's gravity. It is effectively making the Earth's gravity weaker at this distance. Because of that, a satellite that we put in at this Lagrange point will actually be able to travel slower than it normally would. This would allow it to keep the same pace with the moon. So the moon's gravity isn't completely cancelling out the Earth's gravity in the way that you might expect, it's only weakening it enough that the object can stay in orbit at the same rate as the moon. By looking at it this way, the second and third Lagrange points now actually start to make some sense. Both of these points orbit further away than the moon does, and they're able to do so because the moon's gravity adds on to the gravity of the Earth, allowing these objects to move faster than they normally would and keep up with the moon. Finally, we come to the 4th and 5th Lagrange points. When you just look at it, these two don't really make that much sense. They're in the same orbit as the moon, but they trail and lead the moon in its orbit. How is it possible that the moon is allowing these stable positions to exist? Well, the answer comes back to triangles. These 2 Lagrange points make an equilateral triangle when you link them with the Earth and the moon. Because of this, when you add up the force of gravity from both the Earth and the moon, the total gravity that objects in this point feel is in the direction of the center of mass of the Earth and the moon. Because of this, these are actually stable equilibrium points. If we have a satellite in this position and it drifts slightly off course, the way the forces add up actually act to bring it back towards that Lagrange point. The thing to remember is that these points are only stable and only exist where they are because the moon is orbiting around the Earth. If the moon and the Earth were simply held in place in space, only the center point would exist, and even then, it wouldn't exist exactly where it is. Which actually makes the real world more interesting and weird than you would actually expect it to be.